All right, so this one says uses a suitable substitution. So usually if it's under a square root and it's got that square there, we want to use the sine squared plus cos squared equals 1 identity somehow. So for example, we could make let x, and notice we're saying let x, and x is already there. So it's a little bit different type of substitution to what we're used to. We're usually saying let u equal and use a new variable we're bringing in. But here we're saying let x equal, for example, 2 sine theta. And don't forget we want dx. So dx would be 2 cos theta to theta. Now why are we letting x equal 2 sine theta? If we have a look at x squared would be 4 sine squared theta, and you can see there if we factorize by 4, we've got 1 minus sine squared theta, and 1 minus sine squared theta is cos theta. I'll take the square root 4 out, so we've got the square root of cos squared theta, so we just get 2 cos theta. Alright, so when we redo this integral, I'll do it here, we get the whole square root becomes 2 cos theta. Now don't forget, we've also got to substitute in for dx. So go back up to here, dx equals 2 cos theta to theta. So actually I'm going to times that by 2 cos theta to theta. So if I put that together, I get 4 cos squared theta to theta. Now we know that we can't do that so easily, so we just use an identity, which hopefully you're used to from extension 1. So we know that cos squared theta is half cos 2 theta plus 1. So I'll do it in a different colour so you can see. So half, here we go. So cos 2 theta plus 1. We've still got our to theta here. All right, so obviously we've got 2 out the front. Cos goes to sine. But we've got a 2 theta, so the function is 2 theta, so we need a half out the front. 1 goes to theta plus c. Now we have to go back. This is in terms of theta, and we need to go back to in terms of, where's this, a definite integral? All right, let's have a quick look. This is a definite integral, sorry, between 1 and 2. So when we change to theta, we need to change the limits to match. So if I put my x in here as 1, I get sine theta equals 1 on 2. So sine theta equals a half, which we know is 30 degrees. So pi on 6, just put that there. And when we put x equals 2 in, we get 2 divided by 2 is 1. Sine 90 is 1. So that's going to be 90. So pi on 6 and pi on 2 are the ones I need. I should really write those in. So it's, yep, there we go. So pi on 6 there and pi on 2 there. All right, so here we've got 2 outside of, all right, so if we sub 90 in, we actually get pi, so 180 sine 180 is 0. So the first part of that is 0 plus theta, so our theta is pi on 2 minus. Now let's sub pi on 6 in. So double that and you get pi on 3, which is 60. So sine 60 we know is root 3 on 2 times a half is root 3 on 4. And we've also got the theta, so pi on 6. All right, so if we go through that, we're going to end up with pi on 2. If I make it 6, I'll multiply it by 3, it might make it easier to see. So, oops, that's 6. So this is, and I'll put the pi on 6 next to it, and then the root 3 on 4 next. There we go. So we've actually got 3 pi minus pi, so 2 pi on 6, which is pi on 3. And if we multiply that by 2, we have 2 pi on 3. And then I've got minus root 3 on 4, but I'm multiplying by 2, so minus root 3 on 2. So there is our answer. All right, that's by using a substitution. We can also use geometry to do this. So if we look at the actual function here, we've got y equals square root of 4 minus x squared. And if I square both sides and put the x squared on this side, I've got x squared plus y squared equals 4. So looking at this, this is a semicircle, so it's only where y is positive. But not only that, if I have a look at what it would look like, very bad circle. So let's say this circle has radius 2 here. So not only are we just looking at this quadrant here, the limits between 1 and 2. So we're saying the x between 1 and 2. So we're looking for this area here. Now what we can do if we think about that, that is just the area of a quarter of a circle. Area of quarter of a circle. And then we can subtract the area of, so there'll be a triangle there. And then there'll also be, in this other part here, there's a sector. All right, now how do we find those? Well, a quarter of a circle is a quarter of pi r squared, and the radius is 2, so this is pi 2 squared. All right, the triangle, of course, is half the base times the height, the base being 1. What's the height? Well, sub 1, x equals 1 in to get the y value into the equation here. And you'll, of course, get root 3. So let me put root 3 there. The area of a sector is half r squared theta, half the radius is 2, so half r squared. Now, how do we find that angle is what we're looking for there, and we want it in radians? Well, we know this is 90 degrees, so if we find this angle, then we've got 90 minus alpha gives us theta. So how do we find alpha? Well, tan alpha, because we know this is a height of root 3, and this is 1. So we get tan alpha is root 3, just using SOHCAHTOA. So alpha must be 60 degrees. And so then we have pi on 2, 90 degrees, minus pi on 3 to get theta. All right, so we get pi on 6. Yeah. All right, if we put that all together, let's have a look here. We've got 2 squared and a quarter, so this will just be pi. Then we've got minus root 3 on 2. Then we've got minus, and here we've got 4 on 2, so that's 2. And 2 pi on 6 is pi on 3. So we've got a whole pi, take away pi on 3, which leaves us with 2 pi on 3 minus root 3 on 2, which is the same answer. So you can use geometric means, you can use a substitution.